cool looking, slightly like practical room. So I guess we can just start lecture 2 by Jeremy.
All right, thank you again for coming back. Well, let's see. So I guess I'll talk a little bit about motility situations. So whenever you have a map of the infinity rings, say, there's an associated atom spectral sequence. With the one page. And we like the following. And sometimes the two page.
Or if you try to remove the, I don't know why it has this.
I think I may try to remove the microphone.
Remove, and I don't think that's popular because it comes over to the recording, so.
Do we need to?
Yeah, so now should we get out of that problem, then you need to speak
All right.
clearly now.
That's exactly. It was the microphone. Attached.
Yeah, it
is on.
It's on.
This is superior.
Oh, you're okay. Okay, then you can. Okay, we try like this and then. Yeah.
Okay, and sometimes this spectral sequence is a good thing to be looking at, and sometimes it's not, but in particular, sometimes it converges and the YouTube page has an algebra geometric or perhaps homological interpretation. So I want to highlight a particular situation of a B where this will be a very good idea. So given A, we can ask if there exists a B and in that so two things occur. First of all, I want phi star B to be even. So I want all the odd degree homotopy groups to vanish. And second of all, I want that as an A module, B has even cells. So in the this map equips me with the structure of an A module, and I want to be able to obtain B from A in that category of A modules by attaching cells that kill odd dimensional homotopy groups. In other words, even cells. So in such a situation, called the associated atom spectral sequence, the phenotypic spectral sequence computing phi star A. So a couple of remarks about this. In the situation where B has even cells and even homotopy groups, B tensor over A with B will just be a direct sum of copies of B. So everything that appears in this co-simplicial object that forms the E1 page will just be a free module over pi star p. And that guarantees that there's going to be some kind of homological interpretation for the E2 page of the motivic spectral sequence. And the remark is that motivic spectral sequence from the E2 page onwards is not and E or the map A. So in other words, as long as there exists some map of the infinity rings such that this even homotopy in human cells, we get a spectral sequence, and from the E2 page onwards, it didn't matter what B and what map we chose. So that's maybe one indication that this is a kind of canonical spectral sequence when it exists. And one way of seeing that is just to note that this is the spectral sequence associated with the filtered object where I take the limit for all maps from A to R, I start or I Sweden, and the double speed cosmic hotel copy. This I would call the even filtration line. So there's an exercise, an actually very approachable exercise to prove that this limit is calculating the decalage of this atom spectral sequence whenever such a P exists. But here we've written in a way that obviously doesn't depend on any choices. Another thing to say is that the E2 page of the sequence can be calculated as homology of a certain stack. Template powered in some line bundle. And let me tell you what that stack is. That stack is limit over all maps made to right, even. But it's not all. Okay, so if I have a ring that has even homotopy groups, then its homotopy groups actually form a commutative ring. I don't have to worry about the causal sign rule or anything like that, because I'm assuming that these homotopy groups are concentrated in even degrees. So I have a usual commutative ring. It's a graded commutative ring, which means that spec of it has a GM action, and I can mod out by GM. So I can think of spec of pi star R as coming with some kind of canonical line bundle. This quotient by GM is coming with a canonical line bundle. And then when I take this co-limit, I'm going to get a stack with a line bundle, and that's going to calculate this E2 page. So there's a sort of algebra geometric object canonically associated to any even E infinity ring. Say if it admits a map to some B instead.
So you're saying if this that such a map exists, these sequence and columns actually exist.
Yeah, I mean, I think they exist more generally hidden, but you know, when this map exists, they not only do these limits and colimits exist, but they're very explicit and they wind up having to do with this close industrial resolution.
Maybe you can push up the backpack or something. Just like one behind it, just push it up so we can. Yeah. Okay, so you guys like.
So they go too hard. Like you said maybe before your statements. Here's something else. All right, I wanted to do some examples. Look at the sphere. So the sphere is some E infinity ring, and in good cases, I told you that every E infinity ring has some canonical motivic filtration on it, or some, which is some kind of Adams filtration. And so motivic spectral sequence for X. We computed that's nothing to mu. So mu has even homotopy groups by Cohen's theorem. It's also a Tom spectrum over EU, so it's cells as an S module, agree with cells, EU as a space. BU is a space that's even cells, it has some Grassmannian model even. So this is the thing that has even S module cells and has even homotopy groups. And that implies if the motivic spectral sequence is the atom node. It makes these two page, it's the chronology of the moduli stack with formal groups with tensor powers, the canonical line bundle. All right, at least half the time this sport will be up.
Yeah.
But this is a somewhat complicated example in many respects, and the Adams Novikov spectral sequence is somewhat complicated. And I just want to point out that there are other examples that we have already discussed a little bit about, which will be a little more straightforward. So THH of FP, FP joining 0. This has very boring to accept a sequence. Because even filtration on THH is simply the double speed Hahn filtration. So if I come over here, I say that the given filtration is the limit of all maps to even rings of the double speed Posnikov tower. The THH of FP is already even. It's a polynomial ring on this degree 2 generator. And so therefore, its even filtration is just the double speed Posnikov filtration. The associated spectral sequence is the spectral sequence associated with the Posnikov filtration, which is a sort of immediately degenerating spectral sequence. But without P coefficients is another example you would be interested in. That looks like this, at least level of homotopy groups, where this is the degree 2p polynomial generator and this is the degree 2p minus 1 exterior generator. And this no longer has even homotopy groups because this exterior generator is in odd degrees. So there is no initial object in this limit. So we might have to actually do something to complete this limit to understand the monotypic spectral sequence. So how does one understand the monotypic spectral sequence associated to something like this? Well, you have to find a map to some other E infinity ring, which has even homotopy groups, such that that map expresses the target as having even cells over this source. So we can compute the monotypic spectral sequence. Using that from CHHP. Mapping down to CHHP. So at the level of algebra, what this map does is it sends mu1 to mu0 of pth power. Mu1 maps to mu0 to the p, and lambda1 of course maps to 0 because there is no non-zero homotopy groups in CHHP. This thing has even homotopy groups, and what I'm claiming here is that it actually has even cells as a module over this object. And the reason is that there's a little push-out square of the infinity rings. So I claim that this is a push-out of the infinity rings. And one way to see that is again, I have this it's like an interesting isomorphism last time. That this THH can be written as a THH with coefficients in a pi module. And from that point of view, I think this push-out square looks more apparent. Now this map here is the map from an exterior algebra to FP. This is an exterior algebra class in degree 1. And you can just directly see that this has even cells as a module over this by building a little resolution of this as a module of this. And because this has even cells as a module over that, any base change will continue to have the property that the base change of every E will have even cells as a module of the base change of this object.
Sorry, maybe I'm little more. So how, what's your choice of three infinity structure on this theater of the with coefficient in FP?
Well, it's literally this tensor product, if you like. Make you happy. So that tensor product is an E infinity ring.
So this is the same as theater C viewed as the algorithm based into FP.
Yes, I think so. Okay, and so this spectral sequence is not hard to compute, it's just the spectral sequence associated to this map. So you'll learn that this is in Adams grading, if you like. This has filtration 2, 3, 0. And this has filtration 2, 3, 5. So it's a degenerating spectral sequence in Adams grading these numbers. Much simpler spectral sequence than the Adams Novikov spectral sequence. This yeah, this is the same as if I put this no bearing on that object. Okay, and then maybe here I'll write the theorem. Came out of the paper myself, Raxon and Joseph, which says that R is the quasi-syntonic ring, some condition on a discrete ring. You can imagine here that you just have a polynomial ring or a smooth ring that is slightly more general. Then filtration, which requires the motility spectral sequence. Is isomorphic to filtration that it's already defined by someone else in the room. Co-authors, spot knowledge, filtration. Well, this gives a sort of way of accessing the bottom Schultz filtration that is maybe manifestly something that you could apply to THH or some other E infinity ring besides the quasi-symptomic discrete ring, or even things that aren't THH at all. Yeah. So that's how you put the motivic filtration on THH. You just take this even filtration, and the way you calculate it in examples is just by finding these explicit maps. Now I want to talk a little bit about some other structures that exist on THH. From now on, maybe before I forget, I'll say that all that this will be complete. So there's plenty of things one can say before T completion, but probably the most interesting things to say are after T completion. So we'll just go ahead and for simplicity, everything will be T complete. I'll often be thinking about things with path T coefficients and the like anyway. Right. And so now I want to say that if R is an is rel C3 to the infinity equivalent spectrum. Good. Yes, not. Not when CH is the R. Due to the CP geometric fixed points of CH which is the object of copy. CP. So I want to talk about Borel CP to the infinity equivariant spectra as living in more general kinds of CP to the infinity equivariant spectra. I don't want to only be considering Borel objects for reasons which will become clear later. Because I'm key completed, I'm allowed to think about CP to the infinity where you might have expected me to write S1. So to note that the completion with the CP to the infinity is the key completion. Yes, no. So if I'm studying Borel objects, which are maps from these classifying spaces into spectra, then if I'm interested in the P-complete setting, there's no difference between the category of P-complete Borel CP to the infinity things and P-complete Borel S1 things. And this Frobenius map should be need to be infinity like that. Okay, so there is something called genuine THH, but Nicola Schultz told us that there's no data that isn't visible to the Borel THHs. I'm always going to be thinking of THH as a Borel. But the structures that are present are the C2 infinity action and this Frobenius map. Let me make a definition. The lax is the atomic spectrum. C2 to the infinity spectrum. X is the map. It's C2 to the infinity, I think. Okay, so it's exactly the structure that's present on THH. I'm using this word lax just to perhaps emphasize that I am not assuming that this X is Borel. So here I will allow for the geometric fixed points to not equal the tape fixed points. I will not insist that this map is an equivalence, nor will I insist that the geometric fixed points will tape fixed points that have this kind of more general notion. Okay, let's look at some examples. R is the infinity. Is an infinity complex. Then it's category of lax supersonic. Like that. It's the infinity ring that happens to be Borel. There are examples that are not Borel. X, the global, the very spectrum, however, it was not, I will be more specific in a moment. Then there's an inflation map from X to the genuine fixed points. It's part of the so-called global structure. And I can compose with the canonical map that exists always from genuine fixed points to geometric fixed points. And this makes X into X is the common state. We're just using the inflation map. And the example that I want to keep in mind here is mu of CP to the infinity. So there's a thing that was very important to classical homotopy theory, non-equilibrium homotopy theory called mu. And it's well known that in the CP to the infinity equivariant homotopy theory, there's an analogous important object, which is called genuine equivariant Boydism. CP to the infinity equivariant Boydism. Its homotopy groups have something to do with what are called CP equivariant formal groups. It doesn't matter too much what this object is, but I just want to point out that it exists. And it is an example of a lax p-cyclotonic thing, but it wouldn't be an example of a p-cyclotonic thing in the Nikolaus-Schulz's sense, because it is not for a So this is a special case of the previous event. Can you by global equivariant? One more example. Pointer. Animated rings. Good. Let's listen, Thomas Leffler. So I'll call it here, start the first one. And it will be the functor that takes polynomial ring. So there goes THH. So that's a functor, and here I'm thinking about this again as a Borel lattice piece of the atomic spectrum. Something where the geometric exponent is equal to the state. It's left constant. If I want to specify a pointer on all animated rings, I just have to specify what I want to do to the polynomial algebras, and then the rest is forced by the Hahn extension. And then the point here is that is not always the case. THH prism. So we'll discuss this example in more detail in a moment, but of course, polynomial rings are sent to Borel things, and more generally, smooth things will be sent to Borel things. But if I take the quasi-symptomic thing, it need not necessarily map to something Borel, and of course, something that's not even quasi-symptomic could have something that's very much not Borel be the output of this conflict. This map doing things with the multiverse and let's basic atomic second. Say that is I e to the n of b minus 1 b 0 no n to the n to the 0 and b so what is it saying? This is giving a condition on the fixed points of b, or on the C2 to the underlying C2 to the n spectrum of b for every n. And so if I plug in n equals 0 here, this is saying that if I take the underlying non-equivariant object and I look at a complex representation, i.e. an even number, and then I subtract 1, I get when n equals 0, it's this. Underlying spectrum of b. But we're making a condition not only on the underlying spectrum of B, but on all of this restrictions of B to a cyclic group. something to do with these complex representation graded groups. Suppose it's even if my complex representation says as an A module. And sense. I don't expect it's even. So again, in non-equivariant homotopy theory, if I handed you the infinity ring, I said that in favorable cases, there's some kind of very canonical spectral sequence of descent attached to it. And now I want to make an equivariant version of that, and replacements for even integers and even cells are complex representation cells. And then I'm saying that if I want to do this in lattice cyclotomic spectra, I just ask that this be a map of lattice cyclotomic spectra, but I don't put any condition about the Frobenius into the definition of evenness. So as long as this map is good, when you forget about the Frobenius, you just think about the equivariance, then we say it's doing the right thing. Also, with respect to the Frobenius.
That's just a question about spectral sequences of this nature. Specifically, you have like a filtration grading and like a homotopy grading. What are the axes, if you will?
Well, there's a lot of different things you could compute that is descent. So you can write down a co-simplicial object, which has totalization A. And then you could apply all sorts of functors to it. Like you could apply fixed points, homotopy groups of fixed points. So you could apply homotopy groups of geometric fixed points. And I'm claiming that whatever functor you apply to that co-simplicial object, you'll be getting the appropriate motivic spectral sequence converging to the covariance of A.
Try to repeat once more why this is the correct generalization of evenness.
Well, I guess you agree that it is a generalization of evenness.
I guess so, yes.
I mean, in particular, that when n equals 0, you're recovering the previous definition.
Then you want it,
And it's got complex representations of the trivial group are just even dimensional.
right, and then you,
So I would say that the justification for why this is the correct generalization is going to come from its connections to previously defined filtrations, which I'll try to discuss. We're going to see that this notion captures spectral sequences that were already defined in certain cases.
So the point is sort of you only consider complex things, and therefore you always have a two in there somehow.
The analog of even is complex representation. For example, the motivic spectral sequence S same as T adjacent to S. By viewing S as T adjacent to S, I see that it comes with all this structure, like the equivariant structure and Frobenius and the like. This is calculated by the map. MUCP. Right, so again, I said this is a lax p cyclotomic thing. It's not PHH of anything, but it's nonetheless a lax p cyclotomic thing, arising as from a global structure on equivariant borders. This map is compatible with all that structure. It's a theorem. I want to say of Marcus Hausmann, but I think he would say otherwise. This is given in terms of its homotopy grids. And it has even cells because again it's a Thom spectrum over equivariant, the classifying space for equivariant vector bundles, which again has a Grassmannian model in terms of complex representations. Okay, so this is one perhaps reason to believe that this is a good generalization is because it literally captures the analog of the Adams Novikov spectral sequence. And we're playing in THH in the sphere. And now, in the remaining time, I'm going to tell you a little bit about what this has to do with some notions defined by Algebraius, the prismatic polynomial. We give errands. Those are the or the ring. It's a discrete ring that's quasi-regular semi-perfectoid. And what can I say? First of all, this THH prism of R again is defined by animating the Borel THH construction. See them. See the infinity equivariant spectrum.
One question.
Yeah.
Is the sphere with the p-cyclotomic structure, lax p-cyclotomic structure coming from the fact that it's PHH of the sphere, is that the unit in lax p-cyclotomic spectrum?
It is the unit as long as we're working in this p-complete context.
That's also just the map.
Yeah, that's just the unit map. So this is given.
But try FT you mean in over FT, right?
No, I mean over the Z keys.
Then I think that even for perfect coordinates then you would
We can talk about it afterwards. Right, so I think that's correct. And then so I can calculate something. I can calculate the two atoms of the group of the genuine CP to the infinity fixed points of this thing. Limit of the CP to the n fixed points. Thing is that this is the same as the Nygaard equation prismatic homology listed by I. And we can contrast that with what would happen if I took the homotopy response, where I would get same thing. The Nygaard completion. So the claim is that the difference between Nygaard completed prismatic homology and prismatic homology is exactly captured by the difference between genuine fixed points and homotopy fixed points. So there's known to be no difference between these in the case of a polynomial ring, and that agrees with the fact that if you plugged in a polynomial ring, this would be for and similarly, we have a statement about prismatic homology itself. If I take the geometric fixed points, and then I need to the infinity fixed points after applying geometric fixed points. This may be reminiscent of the the construction CPHS1. This is it's supposed to be dramatic in itself. Okay, so that's a connection between this THH prism construction and this algebraic invariance. But so far I've said nothing about the motivic filtration. All I've said is that this animation agrees with these invariants, and that's almost definitionally true because all of these things are in some sense animated yet.
So there you have a 2i and then I occurs twice on the right hand side. What change do you think on the left hand side to get I, second instance of I to not be the same?
But
I'll pick something like get a representation sphere on the left hand side somewhere.
let me think about it before I commit to anything.
When I question what kind of ring was that again?
Quasi-regular semi-perfectoids. This is some very special kind of ring, and I guess we're going to try to talk about more reasonable rings in a moment. But for these very special kinds of rings, these invariants are just sort of almost definitionally read off from this PHH prism.
When you left Alexa and PHH prism into like line speed like does that also change the underlying value of PHH, or is it like do you get any value?
I think the underlying value of THH is unchanged.
Oh, you're just keeping track of some structure.
The things that are changing are the geometric fixed points no longer equaling the takes. The Frobenius no longer just being to the takes. They're factoring through this geometric fixed point. Okay. Right. Then I want to say something about the motivic filtration or the motivic spectral sequence. So if I look at the motivic spectral sequence, so suppose R is now a quasi-symptomic. This is much more general than a QRSP ring, and it's something you can imagine like a smooth ring or a ring that has at worst LCIs invariants. Quasi-symptomic discrete ring. The motivic spectral sequence. We're giving this is homology as E to big. So there's some stack that was defined by Butler and Ginfeld called the R prism. And it's supposed to be some stack such that the homology over that stack calculates the prismatic homology of R. And I gave you a recipe earlier in the non-equivariant case, and also now in the equivariant case for how to extract a stack just given a ring. In this case, given a ring and latch-key cyclotron vector. And the stack you get from this process, essentially by looking at the co-simplicial object over there and applying this functor, DCP infinity, is the prismatization. Similarly, the motivic vector sequence. Order. Megapercent. And you can see the Frobenius and canonical maps coming from the Frobenius and canonical maps and in homotopy theory that will this syntonification if you want to talk about syntonic homology. So this gives a definition of the syntonic homology that been alluded to in the other lecture course.
You just look at the prisms, right? The interprism.
Oh yeah, it's of course. That's the even of this construction, but remember it's a little bit more ubiquitous. So there's a line bundle associated to this, which must do with the fact that homotopy groups are graded rings. And it's tensor powers of that line bundle which come up on this E2 page giving a sort of by degree. That line bundle in the algebraic literature is it's a Brule kiss and twist bundle that gives Brule kiss and twists. Okay, so I wanted to sketch something about the proof. We don't have quite much time about it, right? Let me indicate that a lot of the proof is very easy, except that there are two key facts that are not formal, that one needs the two key facts in proof. First fact, that I like that THH it's also it's the same as THH Z. This is one of these polynomial rings. This thing has the property that square geometric fixed points as well. Well, this is some calculation which I think translated into normal terms. So let's not make it those like please. Maybe that's a pretty residual is zero or something like that, I think. And this is just a calculation one has to do. But it's a certain nilpotent statement which very much helps in analyzing modules over THHZ in this category of lax-free cyclotomic spectrum. So this implies, for example, that if A is in a ring, THH person of A, I think the tricky geometric explains this is actually for so it is very much not the case that THH prism of a ring is 4L, but the geometric base points of THH prism with the residual CQ in the infinity direction are 4L. And it's not something that you would get if you plugged in a random to infinity ring, but it is something that you get when you plug in a Z algebra, and that's very useful. And so if you're familiar with the algebraic literature, you know that these stacks are always formal in two directions, P in this prismatic element direction, I. And so the fact that the result of this procedure is formal in the I direction, in topological terms, it's the statement that this is plural. Okay, so that's one fact. And the other key fact, if I look at the map from the THH of segmenting plus the natural numbers, mapping to segmenting plus the natural numbers, if yes, target the structure of module over the the infinity at the variant thing. If the single infinity plus the lambda numbers. That has the representation of cells. Complex representation cells. So you're familiar with, for example, the work of Antio Cross and Nicholas or EMS2, this use of this map specifically to understand DHH of discrete rings, this is a feature of the so-called fluid kissing descent for understanding DHH of discrete rings. And the fact that fluid kissing descent interacts well with motivic filtration as I defined it, has a lot to do with the fact that this as a representation cells as a module over this. Or I'm imagining this as having trivial CPs in the infinity action. Now, I don't know if I have time to prove that, probably not, but I will just say that when you calculate the cells of this as a module of this, you wind up calculating the cell structure of the classifying space for S1 equivariant line bundles, which again has some kind of Grassmannian model that has representation cells. Maybe that's a good starting point.